Aviation history is full of incredible aircraft that leave us in wonder. But as scientists and engineers, our curiosity goes deeper. We want to understand how these incredible machines fly, what are their limits, and how can we improve them with advanced guidance and flight control systems. Believe it or not, we can answer these questions. Free, online, and open source literature contains a wealth of aerodynamic information ready to be unlocked. This data can be extracted from reports and digitized. When combined with a flight simulation, we create a powerful tool that allows us to investigate aircraft flight characteristics, test new flight control laws, and so much more. The process can take some time, but the payoff can be huge. So join me as we dig into the data and show a process to bring the X-15 spaceplane and many other aircraft like it to life. We'll learn how to extract key aerodynamic data from research papers, build the aerodynamic model, integrate that model into a 6 DOF simulation, and use it to simulate aircraft flight characteristics. Let's consider the process in more detail. We'll need to understand what an aerodynamic model is and how it works within the bigger picture of flight dynamics. Next, we'll dive into the literature for aerodynamic data. Think reports on wind tunnel tests, flight tests, that sort of thing. We'll extract the key aero data from these sources using a handy tool called a plot digitizer. And from the digitized data, we build the database with a custom Python script. The script imports the data, processes it, arranges it in a way that our simulation can understand. You see, the digitized data needs to be interpolated to a common set of breakpoints. We save it in a format that our flight simulator can use. Ultimately, we obtain a database with a set of coefficients that describes all 3 axes of flight. Let's take a closer look at the core of it all, the aerodynamic model. The aerodynamic model is an algebraic function. It receives aircraft state data like angle of attack, side slip, airspeed, and angular rates. It also receives control states, such as aileron, elevator, and rudder deflections. It receives atmospheric data, such as air density and speed of sound. And it provides forces and moments that act on the aircraft that are input to the 6 DOF dynamics. The aerodynamic forces and moments are underpinned by complex flow physics that depend on many variables. That said, there are 2 primary approaches to creating aerodynamic models. First, one can use computational tools, such as computational fluid dynamics, to create a set of tables dependent on many input variables. This approach directly determines the model pointwise, essentially resulting in big tables that are interpolated in simulation. One issue with this approach is the cost of using high-dimensional interpolators. It can slow the simulation down. Further, the database must be post-processed into aerodynamic stability and control derivatives if we wish to gain insight into the physics of the system. A more commonly used approach is the sum of terms, some being from a first-order Taylor series expansion. It does not require high-dimensional interpolators and uses stability and control coefficients that can be plotted for immediate physical interpretation. However, we must acknowledge that we lose accuracy in the aerodynamic model with this approach because we only take the approximation to first order, assuming that forces can be superimposed. The sum of components approach is termed a force and moment buildup. Here, we will use the sum of components approach because the data we extract is in terms of aerodynamic derivatives. The forces and moments are typically resolved in one of 2 coordinate systems. There's the stability axis, defined in terms of drag, lift, and crosswind, and the body axis. The Python flight simulation has equations of motion resolved in the body axes. Therefore, we will need to transform any stability axis aerodynamic data into body axes as necessary. We now provide an example of an aerodynamic buildup for the X-15. The lift coefficient is represented with two terms on the right-hand side. The first term is CL with the subscript WB. It represents the lift force due to the wings and body of the aircraft. It depends on the Mach number and angle of attack and side slip. The second term, CL del E, is the change in lift due to the change in elevator. It's a partial derivative of the lift coefficient with respect to the elevator angle. When multiplied by the elevator angle, it provides the change in lift coefficient due to elevator deflection from the undeflected state. Here's a build-up for the drag coefficient. The definition of the first two terms follow from our discussion of the lift coefficient. In the rightmost term, the subscript delta SB represents speed brake position, computing drag due to speed brake. The side force coefficient is more complex, having 6 terms. From left to right, side force due to side slip, side force due to roll, side force due to yaw, the acceleration derivative or beta dot derivative, side force due to aileron, and side force due to rudder. These coefficients will be transformed to the body axis in our Python flight simulation. There are also 3 moment coefficients with various derivative terms. These are comprised of damping, acceleration, stability, and control derivatives. For further details, see the references by Roscom or Stevens and Lewis at the end of this lesson. In our build-up, we're going to ignore the acceleration derivatives, that is, those derivatives of angle of attack and side slip. Often, these are ignored in aircraft. Placeholders for these derivatives exist in our simulation and may be included in later updates. Now, we've used this build-up before for studies in the vicinity of a flight condition where constant values were assigned for each coefficient. Here, our objective is to expand the aerodynamic coefficient definition to account for changing flight conditions. Let's take this lift coefficient for example. As you can imagine, the lift due to the aircraft wings and body will depend on angle of attack, side slip, and Mach number. Here, we'll focus on the longitudinal plane and assume limited excursions in side slip. Therefore, we go from a dependence on 3 variables to 2. Using a wind tunnel, the aircraft model would be set to an angle of attack with the wind tunnel set to a desired Mach number, and the data would be recorded, post-processed, and the lift coefficient at that specific flight condition would be obtained. The model inclination would be adjusted, and the test repeated to obtain the next desired condition. This would be repeated for all desired angles of attack. And that process would be repeated for the next desired Mach number, and so on, until all data at all desired Mach numbers and angle of attacks are obtained. In doing so, we create a table of lift coefficient data. The values of angle of attack, side slip, and Mach used to create the table are referred to as breakpoints. The breakpoints are not necessarily uniform. For example, if CL had a sharp gradient in a certain range of Mach number, then more Mach breakpoints in that region would be desired to resolve the lift coefficient accurately. Ultimately, a coefficient table is obtained, along with all the other coefficient tables in the buildup, so that the total coefficients for forces and moments are determined. Let's consider the total lift coefficient. For use in the simulation, it must be dimensionalized. The lift coefficient is the dimensional lift divided by a reference force comprised of the product of dynamic pressure, 1/2 rho v squared, and the reference area. To dimensionalize the coefficient, we simply multiply by dynamic pressure and reference area. With this in mind, we can now be more specific about the inputs and outputs of the lift portion of the aerodynamic model. The state inputs are true airspeed, angle of attack, and elevator angle. The atmosphere inputs are speed of sound, denoted c, and used for Mach number computation, and air density. And there's a parameter input, the reference area. The output is dimensional lift. And this is similarly done for the drag coefficient. And all the other total coefficients in the aerodynamic buildup. This is our aerodynamic model. It is dimensionalized and transformed to the body axis so that its output becomes inputs to the 6 DOF equations of motion. We now understand the basics of the aerodynamic model. Therefore, we proceed to search for aerodynamic coefficient data in the open literature. To efficiently identify relevant sources of aerodynamic data, it would be helpful to learn from those who have already created a 6 DOF model. A little over 10 years ago, there were a few papers investigating the root cause of the X-15 crash in 1967. Among the studies is a specific paper by DOF, which we can find from a Google search in MIT DSpace. In this article, it's stated that a full aerodynamic model of the X-15 can be created with the data in these 5 NASA reports. Let's search for the first report. We plug the title into Google, and the first link returned is the NASA Technical Reports server with a link to the article. And in less than a minute, we have it. Amazing. Let's grab the second article by Yancey in 1962. We'll put the title in the search bar in the NASA Technical Reports Server website, or NTRS. It comes up immediately, and we have the option to download. Again, in less than a minute, we have the article. Now that we have identified a set of reports that contains the aerodynamic data, we can extract the data. But since there's going to be a lot of data, before we extract it, we should consider how it will be organized. The data will be stored in our Python flight simulation. The root folder contains the main script run.py, where the user executes specific jobs. The sub-packages are control, where general control input command modules are stored, jobs, where the previous sphere, brick, and X-15 simulations are stored, numerical integrators, vehicle models, where vehicle subfolders containing their aerodynamic data are contained, and tools. We are concerned with how we store data in the X-15 vehicle model. Inside is a folder aerodynamic model. This folder contains the X-15 aerodynamic database, saved as a NumPy array. The build X-15 database script generates this database file. The folder also contains an Excel file, aerosource metadata, which tabulates information about the plots contained in each report. In the metadata Excel file, there are 5 tabs corresponding to the 5 reports. The aerodynamic database was created from Walker 60 and Saltzman 66. Each line in the tab corresponds to a plot in that report. The columns refer to whether or not the plot was used in the 6 DOF, the page that the plot was located on the report or the PDF, which axis the plot was resolved in, whether it's lateral or longitudinal, whether the engine was on, the data that was on the y-axis and the x-axis, and the range of values for angle of attack, side slip, elevator, and Mach for each plot. Creating this metadata file was a useful exercise to understand what was in the extensive report and to identify data that could be used in our aerodynamic buildup. It's also a reference now to locate plot data without having to search through the report page by page. Since each report is a potential source of data, they have their own folders named by the first author's last name and publication year. In each is a plots folder containing JPEG images for each report, and a data subfolder containing a digitized plot file .dig and the exported comma-separated variable file .csv. Now we return to the subject of filling the data folders from digitization of plots extracted from the reports. The main source of aerodynamic data is Walker's 1960 report on theoretical stability derivatives. It is a comprehensive document that includes various derivative coefficient plots useful for force and moment buildups. After we identify the relevant coefficients, we must transform these grainy images into useful tables of data. This task is achieved using a plot digitizer. Among the various available digitizers, I used the Engage digitizer, as it was recommended by a viewer and is openly accessible on GitHub. In the digitizer software, I import a snapshot JPEG file from Walker's report. Let's examine the pitch moment coefficient. The image appears in the workspace, and I'm prompted to give a name to each curve for data export. These will become header names in the .csv file. After adjusting the zoom at the bottom of the page, I set the coordinate system by selecting 3 plot corners and entering their vertices. Using the Curve Point tool, the blue line button at the top, I mark points for the Mach 2 data. Let's switch to Mach 3. Mach 4. And so on. Now, I save this data as a .dig file. Now I can open it later and modify it if needed. And I export the data to a .csv file. Let's open that comma-separated variable file. We see our data digitized. This data will be imported in Python for processing into the aerodynamic database. We are now ready to transform our digitized raw data to an aerodynamic database. Building this database involves several steps as previously outlined. We now go into more detail on what is contained in the Build X-15 aerodynamic database script. Up front, the user selects their desired plots and whether to save the database generated. The desired breakpoints for the database are defined. The remainder of the script performs the following actions for each digitized plot. The comma-separated variable file is imported. the data from the CSV file is extracted. The extracted data is reflected as necessary. Data is reflected here from positive to negative angle of attack with either a symmetric or anti-symmetric relationship as appropriate. The data is interpolated to the desired breakpoints. And finally, one has the option to plot the interpolated data as desired. At the end of the script, all tables are stored in a dictionary with descriptive key names. The dictionary data is saved in the aerodynamic model folder as X-15 aerodynamic database.npz. Here we are in the build X-15 database script. After making the necessary imports, we see the option to turn on plots for each aerodynamic coefficient, as well as the option to save the data. Breakpoints are defined, and then the script proceeds with an enumerated list for each coefficient. For each coefficient, there's a brief description of what it is, followed by the import of the .csv file, assigning CSV data to variables, reflecting the data as necessary using a symmetry or anti-symmetry argument, combining data into arrays, interpolating data to the desired breakpoints, and finally plotting the data as preferred. Let's run this script for a couple aerodynamic coefficients. Let's choose the lift, and let's go with the roll damping coefficient, CLP. The solid colored lines are the extracted data direct from the plot digitizer. The gray lines with symbols are the interpolated data to the desired breakpoints. Note that when the breakpoints go outside of the extracted data, the last data value is held, as opposed to extrapolating the data along the previous slope. Here's roll damping, or CLP, versus Mach number. Again, excellent agreement. These plots are a great way to comprehend the flight characteristics of the vehicle before simulation, and they can be used to verify expectations of the simulation. If the aircraft does not behave as expected, the root cause should be investigated. So as we scroll down to the bottom of this lengthy script, we come to where we store the tables in a dictionary along with the breakpoints, and then finally save the data if chosen. The build aerodynamic database uses custom interpolators, FastInterp1 and FastInterp2, specifically designed for fast 6 DOF simulation. We now briefly explain the custom FastInterp2 function. Interpolation is used multiple times at each time step of a simulation, so efficient interpolation is crucial for the simulation to not bog down. Here's an excerpt from the flateartheom.py script performing interpolation just for the moment coefficients to the instantaneous Mach and angle of attack. In flight simulations, interpolation is usually only needed to a single point, while interpolators are usually designed to handle arrays of data. In my experience, many interpolators take significant time, slowing the simulation, presumably due to the overhead of handling data arrays or building in other features. Therefore, I wrote a custom bare-bones interpolation function for the Python flight simulation. This allows rapid interpolation to single data points. To illustrate how it works, consider this true image produced by evaluating a specified two-dimensional function within a restricted domain. The black margin in the plot indicates the absence of data. This represents a coefficient table in our aerodynamic database, and the margin is hypothetically flight conditions that could occur, but where no data is available. So our interpolator objective is to interpolate accurately within the given data set and hold nearest neighbor values outside the data set. While going outside the coefficient tables in simulation should be avoided, a nearest neighbor approach is preferred to extrapolation. Because not only does extrapolation try to predict what we do not know, but extrapolation for the large number of coefficients in our buildup can produce erroneous results. We first test the grid data interpolator available in the SciPy package. Within the restricted domain, interpolation produces a similar image by visual inspection. Outside, we observe gradients in color along the extended rows and columns as opposed to held values, indicating extrapolation. Instead, we desire data outside to be its nearest neighbor value, which is not an option of grid data. I designed our interpolator to assign the nearest neighbor value. If the data is to the left of the first column outside the X domain, but in the Y domain, then we assign the nearest left column value to the data point. A similar rule is applied to the other three outside row and column regions. If the interpolation point falls in the outside corner, for example the top right corner, then we assign the corner value of the data table. The other corners hold in a similar fashion. Now, comparing the custom two-dimensional interpolation routine simply called FastInterp2 to the true image, we observe agreement as with the grid data function. The FastInterp2 function uses bilinear interpolation and again only operates for a single point. Outside, we observe the nearest neighbor values held along rows and columns and into corners. The interpolation routines and test case scripts are provided in the Tools subfolder. Presently, only 1 and 2D interpolation routines are provided. We're now at the final stage, integration of the aerodynamic database in the Python flight simulation. When we integrate the aero database in the simulation, we update the contents of two folders, the corresponding jobs folder and the vehicle model folder. In the job folder, we update the equations of motion script. In the vehicle model, we make a new function in the X-15 vehicle definition, specifically for the updated aerodynamic database. We call it X-15 Rev3. Previous X-15 model versions are unchanged to ensure those jobs will run as before. Here we are in the X-15 vehicle model script. Scrolling down, we arrive at Rev3, where we see the loading of our aerodynamic database. Then further down, we see the assignment of the coefficient tables and the breakpoints out of the dictionary into similarly named variables. These tables are then stored in the vehicle model, or VMOD for short. It's another dictionary, and in addition to the breakpoints and coefficients, it contains mass, inertial properties, and other properties of the aircraft. In the equations of motion script, we find the assignment of the coefficients and the breakpoints out of the VMOD dictionary into new variable names, again similarly named to the keys in the dictionary. These are input into interpolation routines to evaluate from the tables the coefficient at the present flight condition. These interpolated coefficients are input into the force and moment buildups, and the simulation proceeds as it has in the past. Looking to Yancey's 1964 report, we find longitudinal and lateral flight test data for the X-15. Take this figure 5 for example. It's the time history of longitudinal oscillation resulting from a stabilizer pulse. Here, engine power is on, and the pitch stability augmentation system is turned off. The lateral SAS remains on. We can test our simulation against this flight test data. Here we are in the job subfolder that seeks to simulate this flight test. Our goal is to find a reasonable comparison between the simulation data and the flight test data. Let's go to the sim config file. Scrolling down, you can see we're using revision 3 of the X-15 model with the updated aerodynamic tables. The flight test data was extracted from figure 5 with the plot digitizer. And this data was used to identify the initial conditions for this simulation. We import the elevator time history, and we set the aileron and rudder inputs to 0. Since the elevator time history is the result of stability augmentation system or SAS settings, in our simulation we should turn off the longitudinal SAS. But since the pitch SAS gain was 0 in the flight test, it ultimately makes no difference here. Let's run the simulation and compare the results. We see oscillation in the angle of attack. Here's a familiar elevator time history. Oscillation in pitch angle, lateral, Euler angles 0. Oscillation in pitch rate, similar in W velocity body. And we observe the short period oscillation in the X-15. It's difficult to compare these results to figure 5 in Yancey's report. So there's a script in the job that specifically does that. Compare 6 DOF to FT. We find excellent agreement in the short period oscillation frequency and amplitude as evidenced in the angle of attack and pitch rate plots. We find a significant difference between the Mach and altitude histories simply because we do not have a rocket engine model in our flight simulation yet. Our 6 DOF sim shows less damping of the short period than flight test data. Nevertheless, as a model being compared to a real physical system, the agreement between the two is confirmed. Back in Yancey's report, we find figure 6 contains a lateral directional response from an aileron pulse input. This time the engine's off and all channels in the SAS are on. Again, our goal is to find reasonable agreement between flight test and simulation data, now in the more complex lateral plane. The initial simulation results were very different from the flight test data. We observed our simulation predicted divergence in side slip, in contrast with the stable flight test result. The simulated roll rate significantly exceeded the flight test. We also saw better preserved altitude and Mach in the simulation compared to the flight test. Let's take this one thing at a time, starting with side slip divergence. It's speculated that small rudder deflections are at the source of the side slip divergence. So to test this, we'll turn off the rudder in the simulation and compare the results. We find significantly less growth in beta with the rudder off, indicating that the rudder plays a role in side slip divergence. This leads me to suspect one of the rudder control derivatives. To test this, we inspect the simulation and verify there are no unit errors. Also, we verify the value of the theoretical rudder derivatives, CY_r and CN_r, derived from the Walker 1960 report, to the experimentally derived rudder derivatives in Yancey's 1964 report. We find no issues and conclude that the rudder derivatives are not playing a role in the side-slip divergence. Since a noticeably larger roll rate is shown in the bottom plot than in flight test, the next thought is that roll rate is coupling into yaw through CNP. So we turn off CNP, yaw moment due to roll rate, and find that the results are visually indistinguishable from the previous simulation. We therefore conclude that roll rate is not the source of the side-slip divergence. And then bam, a unit conversion error. While working through the tests, I realized that CN beta with units of 1/degrees was incorrectly converted to 1/radians by multiplying by pi/180. The conversion factor is 180/pi since degrees is in the denominator. But it didn't stop there. CY beta and CMQ had the same conversion errors. So these errors, particularly 1 and 2, become obvious suspects behind the divergence in side slip in our simulation. And suddenly, when corrected, although much more damp than the flight test data, side slip does agree better. It does not diverge. However, the damping is increased, and that could be due to other factors. So we set this concern aside and cross off side slip from the list. Now, on to roll rate excursion. One possibility is that CL beta, that is roll moment due to side slip, is incorrect. We checked the units and compared with experimental data and found no issues. Another possibility is that roll moment due to roll rate, CLP, or the roll damping derivative is too small. So we checked units and compared with experimental data very carefully, but we found no issues. So we concluded that CLP does not contribute to the roll rate excursion. Perhaps we have excessive moment created by the aileron, so we question CL del A, the control derivative. Again, we check units and compare with experimental data. Here's the extracted data from Walker 1960. The Mach number is 3.4 over the 5½ second duration of this flight test. This gives a computational CL del A with units of 1/degrees of 0.0012. Yancey's 1964 report contains this derivative determined from flight experiments. Mach 3.4 gives CL del A in units of 1/degrees of 0.0006. Whoa, the flight test data shows the computational predictions at this Mach number are off by 50%. This must affect the simulation. So, being the good scientists that we are, we carefully state our hypothesis. The overprediction of the computationally determined CL del A contributes to the roll rate excursion. To test this, we put a scale factor of 0.5 on CL del A to represent the 50% reduction in known control effectiveness from the experimental data. The results significantly reduced roll rate excursion, but not all the way. We conclude that CL del A did indeed play a role, but is not the sole cause of the roll rate excursion. But there's more to this plot. Let's focus on the first 1 second. We see a tale of two timescales, visually distinct at 0.5 seconds. Before 0.5 seconds, we see a fast rate of change that almost perfectly follows the flight test data. This is due to the aileron pulse, which achieves its peak value just before 5 seconds. The corrected CL del A seems to have corrected this rate of increase. But after 0.5 seconds, Instead of roll rate subsiding, it slightly increases. This is evidence that our system is underdamped. Somehow, the flight test exhibited significantly more damping in roll than our simulation is providing. This could be due to yet an unknown bug in the sim affecting the roll channel, or an issue with reporting the flight test data, or both. Regardless, we can postulate there's an unknown source of damping that's not captured in the simulation due to a bug or otherwise. To test this, we can tune the roll damping derivative and see if it matches the flight test. After some trial and error, we find a factor of 10 on CLP best corrects the simulated roll rate. So, roll damping does seem to be a source of the discrepancy is the conclusion. At this point, we halt further investigation until roll rate and move on. There are many other flight experiments we can compare to that'll help us uncover the reasons the simulation and the flight test may disagree. What about the longitudinal dynamics in this simulation? While the longitudinal dynamics easily decouple from the lateral dynamics under a steady wings level assumption, the lateral dynamics only decouple under steady wings level with small state perturbations. If we violate the small perturbation assumption, we must also capture the longitudinal dynamics coupled to the lateral for accurate lateral dynamic prediction. Searching through Yancey's 1964 report, the source of our lateral flight test data, we find a table that lists all of the lateral directional maneuvers involved in the study. Now, we pulled our flight test data from figure 6, but there's no explicit connection of that figure to one of the cases listed here. Our extracted data, however, puts us at Mach 3.42 with an initial altitude of 81,455 feet. And the caption of the plot says the SAS had roll, pitch, and yaw gains of 8, 6, and 8. This leaves two possibilities highlighted in the table, one with the speed brake open and one with the speed brake closed. Since the initial altitude was closer to 80,850 feet for the case of the speed brake closed, we assume that's our case identified in the table, which sets the angle of attack initially to 7.3 degrees. Here's an excerpt of the sim.config file where the initial condition data is provided. Now, angle of attack is 7.3 degrees. This gives the aircraft as shown in the longitudinal state. But what about pitch angle? Was the aircraft flying parallel to the horizon as shown? Probably not. Although pitch angle is not reported, there's a way to estimate it. From the altitude versus time plot, we estimate the rate of ascent as minus 925 feet per second. For altitude between 76,000 and 81,500 feet, the speed of sound is approximately 977 feet per second. At Mach 3.4, the X-15 true airspeed then is 3,323 feet per second. The velocity vector is oriented such that the vertical component is minus 925 feet per second, according to the rate of ascent. Therefore, the aircraft is descending, so the flight path angle is negative. Since pitch angle is angle of attack plus flight path angle, we'd like to solve for flight path angle to approximate pitch angle. So solving for flight path angle, we obtain minus 16.2 degrees. Therefore, the pitch angle is minus 8.9 degrees, and this is used as the initial condition in our simulation. Our vehicle longitudinal configuration therefore changes from 0 pitch to minus 8.9 degrees pitch. Now we're prepared to test the idea that the longitudinal dynamics couple into the lateral dynamics. Our test is to run the simulation for the updated angle of attack and pitch angle initial conditions. We find the altitude trajectory now matches the flight test nicely. However, the Mach number is still over-predicted. Also, the side slip oscillation or Dutch roll mode still does not match in frequency or amplitude. However, altitude versus time is mostly overlaid on the flight test data. Mach, however, is preserved, differing from the flight test data. we conclude that the longitudinal dynamics do couple into the lateral dynamics, and the update to the initial angle of attack significantly improved the simulated altitude, although the mismatch between Mach number indicates under-prediction of drag coefficient. So we cross off altitude from the list. Now recall that this simulation assumed the speed brake was closed, but based on the slightly increasing Mach number, now I speculate the speed brake is likely open. If so, the angle of attack should be 2.6 degrees, and determining the pitch angle, we get minus 13.6 degrees. From Saltzman 1966 report, at Mach 3.4, the drag increment due to the speed brake fully open is 0.06 to 0.07. Adding this to the drag coefficient from wings and body will more than double the total drag coefficient. Running the simulation, we find the Mach number now decreases, matching the flight test data better, but it appears drag is still underpredicted. We conclude the speed brake was likely open during the roll pulse lateral flight test captured in Figure 6 based on this result. Here's a visualization of the aileron pulse maneuver. It's quite modest when visualized given the dynamic looking signals we've been investigating. Having gone down the rabbit hole of validating lateral dynamics of the X-15, let's take a step back and remember the goal of this lesson. It's to show the process of creating an aircraft aerodynamic model from data in the literature. And we integrated that model with our simulation, and we did some validation of our X-15 spaceplane against flight test data. So this is a great start to model validation. But the investigation also highlights the challenge of resolving simulation predictions against real flight test data. As George Box famously said, all models are wrong, but some are useful. As an educational tool, the aerodynamic model in this simulation is certainly useful. As a predictor of true X-15 flight dynamics, well, further investigation is needed, including testing the simulation against other flight test data. In this lesson, we reviewed an aircraft aerodynamic model using the X-15 as an example. We searched for aerodynamic data in open reports, extracted plots, digitized the data, and organized it, subsequently processing that data into an aerodynamic database. This involved interpolators, and we explained custom fast interpolation routines developed for fast 6-stop simulation. The aerodynamic model was integrated into the Python flight simulation and then evaluated against flight test data in the literature. While the longitudinal dynamics agreed well, the more complex lateral dynamics initially differed significantly from the flight test. This led to considerable investigation, ultimately resolving many of the differences, but leaving room for improvement. The Python flight simulation and the X-15 6-degree of freedom model it contains is a useful tool for future guidance and control studies. Access this lesson and more at learngnc.com. To all my subscribers, YouTube and Patreon, thank you very much. And particularly to my Patreon subscribers, thank you for your support. Without it, the development of this lesson and the other lessons I've produced just would not be possible. I hope that the lesson codes you receive help your educational experience. So if you're interested in supporting the channel, gaining access to the codes and other educational content, consider subscribing to Learn Guidance and Control on Patreon. The codes for every lesson I produce on YouTube are made available. That's all for now. Good luck. Until next time.